Hello, I'm Ayush Guraria with Diego Bermudez and Santiago Bolanos. We present our project on exploring EEG image classification and caption retrieval. Let's start with the problem. The core questions we are asking is, can we decode semantic meaning directly from brain signals? We know that classifying EEG into broad categories is possible. However, the big unknown is whether we can map noisy EEG data into a structured multimodal space like CLIP to enable direct EEG to caption retrieval. Why this matters is because it would shift brain computing interface from simply selecting buttons to conveying abstract meaning, effectively bridging biological vision with modern AI language models. Let's look at the project tasks. We broke this challenge into two distinct tasks. The first task is our baseline. We train an encoder to classify images into 20 categories, ensuring we can extract discriminative features from the raw EEG. Task 2 is the main contribution, projecting those EEG features into clip text embedding space to retrieve the correct caption for a given visual stimulus. Let's look at the data. We use the Wong et al. 2025 dataset containing datasets from 13 subjects across 5 sessions each. This multi subject nature introduces significant variance that our model must handle. This input is a time series matrix of 122 channels by 500 time points, pre-processed with standard filtering. Let's look at the approach now.
So we design a three-stage hybrid encoder, moving from local feature extraction to global context, and finally subject-specific calibration. Here's the detailed view. So in stage one, we use multi-scale 1D convolutions for temporal features, followed by a linear projection map dimension to map the dimensions. Then in stage two is a shared transformer backbone that learns universal visual patterns across all subjects. Finally, in stage three, we branches that into 13 separate heads. And train this, we use a selective backpropagation where gradients update the shared backbone, but only the specific head for the current subject is updated. This prevents negative transfer between subjects. For retrieval, we freeze encoder and train a projection MLP to map embeddings into the clip space using info-INCE contrastive loss. Finally, instead of expensive full fine-tuning, we use LoRa, short for low rank adaptation, on clip. We freeze the weights and inject trainable rank matrices, allowing the semantic space to adapt to the EEG manifold efficiently.
Moving to our results, we used a deep encoder with 6 layers and 8 heads and heavy dropout, meaning 0.4, to combat noise. For clip, we used a rank 32 LoRa. Our retrieval results show recall scores near 0. These negative results is scientifically significant. It indicates that, despite a working classifier, the domain gap between noisy EEG and structured text embeddings is too large for a simple projection. Analyzing a failure case confirms this. For Dinning table input, the model retrieves completely unrelated concepts like bulldog. The embeddings are currently not clustering by semantic class. Why is this so hard? Well, the main issue is data scarcity combined to geometry mismatch. 26,000 trials are likely insufficient to align these distinct manifolds from scratch. To fix this, we propose three architectural changes. First, using deep residual network instead of a simple MLP. Second, applying LoRa directly to attention layers for deeper adaptation. And finally, adding a hybrid loss with direct cosine alignment. In conclusion, while fine-grained retrieval remains a challenge, we successfully implemented a robust multi-head hybrid architecture. We established a computational baseline and identified that the embeddings alignment stage is the critical bottleneck to solve for the future semantic BCIs. Thank you so much for listening. We're eager to receive your feedback.